Hello. Very little of me directly in this one. I think I'd like to skip straight to my browser. Right. So my goal today is to show off some ways online of demonstrating Fourier series. So what I did, you can see here, is literally just Google Fourier applet. My favorite one is this top one, the Fourier series applet. Some of these just copy that basically. So this first link is pretty good. And I also like this FET one here called fet.colorado.edu Fourier making waves. Now, one unfortunate thing about that, I'll show you what happens when you click on that tab. This is a legacy simulation, which means it uses Java, and my computer doesn't like it. My old laptop, which I got very soon after joining the faculty here, right? It can handle that, and that does some things visually a little bit better, but can't run it here. So I'll try to capture a few minutes of that on the other machine and post that as a separate video. So these are the options that we have, and what my slides talk about. I don't know how much slide work I'm going to do, independent of this stuff. But one thing, the whole point of this week is set to demonstrate is Fourier's theorem, which is that any repeating waveform can be made up of sine waves and cosine waves. Cosine waves are just sine waves that are shifted a little bit in phase. So the good applet is something like this, and I'll do some microphone manipulation here. You'll see if I turn it backwards, you can't hear me as well, but you're now pointed toward my speakers. So I can play a sine wave. Hopefully that came through. Don't mean to make this too loud, but here's what the sine wave is. Okay. Now I can shift to a cosine wave here. So if you notice the difference between these, the waveform is exactly the same shape. The sliders we'll see more of a little bit later, but they're just pretty much controlling the amplitude of different sine and cosines. And they don't sound any different. So there's the sine, and the cosine sounds pretty much the same. And I can make up other waveforms too just by clicking on them. You'll notice that the cosine wave can convert to a triangle with a click of a button. And the waveforms look very similar, except you'll notice the points are a little bit sharper and the sound is a little bit different. Okay, so that's clearly not a pure tone there. You can try this on your own speakers when you're playing around with this stuff yourself. Okay, there we go. I sound a little bit better. So, right, we can do sine and cosine and triangle. There's also the sawtooth wave, something like this. All right. We can do a square wave. And then there's some other options. Some others I like seeing, right? There's the sine wave. We can rectify it, which means takes all the negative portions and cuts it down to 0. Or there's the full rectifier, which takes all the negative parts and makes them positive. These are things, if you play around with diodes in an electronics course, you can build circuits that do this to input signals. All right. So you can click a number of these things, and a main point is whichever one you choose of these presets, the computer will know what mix of sine waves to put in. So, right, Fourier's theorem says that we can build up any repeating waveform with sines and cosines. You can even draw on this as well. I can just make up a signal like this. The computer will repeat it for me, and it will tell me the mix of sines and cosines that you need to get this done. At least the best approximation that we've got. Now, going back to something simple like a sawtooth, one thing that these sliders demonstrate is, right, if you take, this is a fundamental frequency. Remember, we can take different amplitudes and phases of all of the harmonics and make up this pattern. So the sawtooth wave that's drawn in red is made of this sine wave, and this sine wave, this one, this one, this one, and this one, this one. And it goes all the way down infinitely, all right? The more of these you add, the better approximation to a slanty perfect straight line here. Okay. Some other things you notice, the triangle looks especially good. It doesn't look particularly wavy. And notice that the triangle, the transitions are fairly smooth at the top and the bottom. For the sawtooth and the square, you might notice at the very tops, you have these little protrusions, almost like devil horns up there. That's a phenomenon called the Gibbs overshoot. And that comes about because in these waveforms, you notice we always have these abrupt transitions from the highest to the lowest, right, happening basically instantaneously. It's like a jump in the function. And when you're trying to use sines and cosines to make functions that have jumps in them, even the best attempts won't get rid of this little overshoot you have at just the edges. It's around 8 or 9% overshoot at those two ends. So the sawtooth and the square has it. Since the triangle basically goes, I mean, the lines are slanted, but there are no giant jumps. You don't have that feature. Okay, so a couple of things to explore. I'll do this better. This is why I like the other applet in some ways, because I have better control over this. But what we can do is we can look at what kind of waves, right? What kind of waves the computer says makes up this sawtooth, because okay, we can hear it. Okay, it's obviously a very buzzy noise, right? But why is it like that? It's like that because we have these higher frequency overtones or these higher frequency partials mixed in. And as my slides discussed, those higher frequency partials are, they're related to the fundamental frequency. They're often real notes in the actual scale. So they're not just random frequencies, but they're mixed in there, and they help contribute to the timbre of this waveform. And what we can explore here is for the sawtooth wave, we have an alternating series of these. So you might notice the number in front, that's the amplitude here. And the amplitude is technically a positive number, but some of these here have a negative sign in front, which means that starting from the origin, the sine function starts off going down instead of going up. It's a different phase choice pretty much. And we can look at how big each of these waves are by looking at the size of the number. So this is our fundamental. It is something like 0.64. And this one's about negative 0.32. So you notice the size of this is about half. This one's about 0.21, so that's about a third. This one's about 0.16, so that's about a quarter. That's 1/5, 1/6, 1/7 of whatever amplitude this is. So in this sense, these waveforms we're kind of using a recipe to figure out what's going on with these things. It's like you take one part of the fundamental, then half of a part of the next harmonic up, then a third part of the next harmonic up, and you flip the even numbered ones upside down, right? And so the computer is doing this automatically for the first 34. I can make it do a lot more terms. It's a little obnoxious, but let's see, I can make it do 48 pretty easily for the sawtooth there. Right. I could even cut this off at I could cut this off at a smaller number of terms, like 9. Okay, so when I do that, I still get a sawtooth wave. You can see the overshoots a little bit, but the wavy character in the middle here is a little bit more apparent. So the more and more of these terms I add, And I'm not adding much of these other ones, but the more and more I add, the flatter and well, the more steady and increased this is. You still have those overshoots in the top. All right. Now, what I can also do is let me demonstrate how the recipe might go. I can make this one 1, and this one -1/2 approximately. Can't do this perfectly. This is one thing the other applet lets me control a little bit better with my typing, but this is the third harmonic, so that's why there's the 3x in parentheses there. So that's about a third and a quarter, and I'm getting as close as I can, about 1/5, 1/6. Not gonna overthink it. Okay. And so that's just me approximating 7 terms of this series using the recipe. I could, in theory, if I had a program that let me use an amplitude as high as 2, I could, so to speak, double the recipe, make this 2, make this 1, 2/3, 2/3, 1/2, 2/5, and so on, and get a sawtooth that's double. Right. I also have played around successfully. If I make all of these positive, you get a saw that's going the other way, roughly. So that's another option that I have. And another thing I can do, here's the built-in sawtooth wave. If I shift this a bit, so it's like about there. Yeah. You get all signs again, but they look a little bit different. And if I go about here, that's roughly what I started with. All right. There's some other functions we can play with too, and I encourage you to explore what these are. Let me look at the square. So here's a square, and let's see what we notice about the square. This one, again, is made up of all sines, and check this out. So it's made up of this big fundamental frequency, and the second harmonic is gone, and it's made up of a bit of this third one, and the fourth harmonic is gone, and the fifth is there, the sixth is gone, so on. So I mean, that's something to notice, that you can make a square wave, right? The sawtooth included all of the harmonics, and the square only includes the odd ones. So let's see how much of each there is. This is about 1.27. This is about 0.42, 0.43 or something. So that's a third of the amplitude. So we mix in about a third of this one, 1/5 of this one, 1/7 of this one, so on. It's kind of neat. It's as though, let me cut this down a little bit. It's as though we take the recipe for the saw, and we just take all of these even ones and we remove them. And the ones I'm removing first have less an effect, but watch what happens when I remove this one. Like the sound effects. Okay, so right, I took something that was a saw and I removed all the even harmonics, and you end up with something that looks like a square. And here's this is just a more precise one with a higher amplitude. And if you add more terms, it looks better and better and better. So the sawtooth recipe and the square are related. The square is just the same mix as the saw, but all the even harmonics are removed from the mix. So that contributes to differences in the tone you hear when you listen to those two. Briefly playing both. All right, so the saw, that, the squares like that. So they have different timbres to them. You could train yourself to identify the differences in those. There's also the triangle, which we'll look at. We can hear there the difference between a sine wave and a triangle. Um, those two sound the closest, actually. The triangle sounds much closer to a pure tone than the than the uh, than the saw and the square do. In this case, the computer gives me, well, first of all, I got to comment, this is a beautiful triangle wave. And the computer gives me a mix in this case, which is all cosines. So that's something that's worth showing. Um, look at what I start with. Actually, one simple cosine wave just about covers it. Actually, look, I mean, you gain a little bit of amplitude around the corners, but this is why, right? I mean, the triangle just visually looks like a cosine almost with some pointy bits. So we have this one that's 0.81 in amplitude. And again, the even one is gone. 2 is gone, 4 is gone, 6. So we don't include those. And look what we have. We have 0.81, and the third harmonic is 0.09. So that's actually one ninth of the amplitude of the first one. And right, this is how we describe the recipe. Remember, with the square, I would take the fundamental amplitude and divide by 3 to get the third harmonic amplitude, and divide by 5 to get the fifth harmonic amplitude. Like, right, 1.27 divided by 3 gives you this. 1.27 divided by 5 gives you this. For the square, for this, no, sorry, triangle. Triangle. 0.81 divided by 3 squared gives you this. 0.81 divided by 5 squared gives you this 0.032. Right? So already at the fifth harmonic, we're barely adding any more higher frequency wave to this. And we don't have to, because the triangle and the basic cosine wave are already so similar. Right? So that's a demonstration of some of the recipes. Now, one further thing to show is right, what's the difference between these sines and these cosines. So a basic sine and a basic cosine look like this and this, that and that. Okay. So they're the exact same shape. They're centered in different places. And another thing to notice about these functions is that the cosine is symmetric around this middle line here, around this y-axis. If you go to the right from this and look at the value of the function, and the left the same amount, and you look at the value of the function, they're going to be the same. There's perfect symmetry around this. And cosines are a type of function called an even function, which has the symmetry. Sine functions are called odd functions, which have the feature that, right, they go through the origin, and if you go some direction to the right and look at where the function is, if you go the same distance to the left, the function is doing the opposite thing. So if I go a little to the right and up, you get the maximum. If I take the value of the function a little bit to the left, that's the minimum right there. So sines are odd functions, and cosines are even functions. Now, if you look at Wolfram alpha, which I think I've demonstrated to the class before, odd and even functions I consider called this because if you graph a polynomial that only has even exponents in it, it's going to be an even function. And if it only has odd exponents in it, it's going to be an odd function. So check this. I just graphed y equals x squared. That's a parabola, which you've seen before. Technically, even I can add something like, 5 times x to the 0. That doesn't really, right? X to the 0 is just 1. So it's like I'm adding 5 to this. I'm getting the same, I should get the same shape parabola. You notice I do, but it just starts in a different place. And this is still a symmetric even function. If I go, if I go 1 to the right, I'm at 6. If I go 1 to the left, I'm still at 6. The whole thing is shifted up. So when you look at this, applet, the, the cosine set has actually just a plain shift up or down that you can combine. You can still get an even function when you combine this piece, right? Or you add that piece to the function, you can still have an even function. And then I'll just play around with it. If I add another component that has an x to the 4 term in it, right? You notice I'm only putting in terms that have x to an even power. Hoping this could load a little bit faster. Yeah, it does. And it graphs it for me. And right now the whole shape opens down because this x to the 4th term, it dominates pretty quickly if x gets big or small enough, but the function is still symmetric around this y-axis. And this is an even function. Now if I do the same and replace with odd exponents, like x to the 1 and x cubed. Okay, I enter it and Wolfram Alpha, nerds out on me a little bit. It graphs the functions for me. This is an odd function. You notice if you go one direction, it's positive. If you go the other direction, it's negative. It's like you can rotate this 180 degrees around the origin and you get the same function. So functions that are polynomials using only evens are even functions, and only odd powers of x give you odd functions. In fact, sine and cosine, which were my original examples, in calculus you can learn that sine and cosine can be written as polynomials as well. Like if I did well, like this first example suggests something, right? If I take x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, you get something that for a short amount of time looks like a sine function. And then let me just put in another term or two. This is something called a Taylor series. I'm just adding some more terms in there. And see that the more and more of these I add, that means the function is odd and it blows up here and here still. But the more and more terms that you add, the more and more you get something that looks like a sine function. And similarly, there's a combination of even functions, like 1 and x squared and x to the 4th. There's some mix of those which give you a cosine function. So may not seem like sine and cosine are related to algebraic polynomials, but they are. All right. So if you have a function and you look for its symmetry, you can tell whether it's going to be made of sines or cosines. So one example is this triangle. So this triangle is an even function if you look how it's symmetric, and it's only made up of cosines. But if I phase shift this, so it's like about there, okay? So if I phase shift it, so the same triangle is an odd function, now we're making it with sines. And the recipe is roughly the same. You have 0.81 of the fundamental, about 0.09 of the third harmonic. And so, right, the mix of harmonics is about the same, but by making it into an odd function, I can make it all about sines, right? So that's about all I want to demonstrate for this app for now. I'll do a quick screen capture of the other one on my old machine that can handle it. For reading that I'm going to include, not necessarily reading, but some videos that work, is another introduction to Fourier series is a video from Khan Academy where they draw it out and show we can approximate a repeating function with sines and cosines. And even fancier is the 3 blue 1 brown video called But What is the Fourier Transform? So that one gets way more complicated, way more quickly. And that has mathematical detail that is well beyond anything that you're going to be asked to do. But three blue, one brown, even though he's fairly young, under 30, he started out working for Khan Academy and then quit to focus on this channel because his narration and animation were too good. So that explains it. And there are other ways of visualizing this too. I found another animation of how we can show how sine waves make up something like a square. This is an animation showing a square wave using the first four terms. And it's a cool visualization. So the blue circle represents the motion of the fundamental. And right, the third harmonic is 1/5 as big. The fifth harmonic, the third harmonic is 1/3 as big. The fifth harmonic is 1/5 as big, and the seventh is 1/7. You can see that with the 3, the 5, and the 7 in the denominators of these functions. And if you combine them all together, you can visualize how maybe a square wave comes out of this. The three blue, one brown video does a pretty good job of showing this off too. And that video also shows how you can take a mix of signals and analyze their frequency components, trying to find with the thumbnails how or where you see this occurring. All right, like you can take two notes that have different frequencies. When you add them together, you get a more complex wave, and it's possible to take the complex wave and figure out in reverse what are the frequencies that make it up. It's Fourier analysis, pretty much what that is. So I won't show those videos here during this one. Really, my point was to show off this applet, which you are free to explore a bit yourself. So I might put up a video of some slides summarizing all of this, and a screen cap of the other applet, which has some visual elements that I like. I think I'll stop here for now, right? So.